Thank you for joining this webinar. This webinar is focused on how to find stories in your survey data. As always, I'm presenting in Displayr as it's designed for presentations, but everything I show you other than the AI can be done in Q as well. If you want to follow up on any specifics, ask at the end in question time, and I'll show you kind of the steps in Q. As you go, if you have any questions, please type them into the questions field in the GoToWebinar app, and I'll get through to them at the end. We will send you a recording of this webinar as well. The first step in finding the story in your data sounds a bit boring. It's to create and implement an analysis plan. Typically, this involves the creation of hundreds or thousands of tables of data. And it's the easy bit. The next stage is to reduce all of the data so that all that is left is the interesting stuff. This second stage, known as data reduction, is the main focus of this webinar. It's a natural thing when you've collected data to just jump in and play with the data. However, as a pretty general rule, when people do this, they end up getting lost and finding no story. The smart way to proceed tends to be to have a written analysis plan. There's something about writing an analysis plan that focuses your mind. We'll start by looking at an analysis plan for a study investigating the appeal of this product, the iLock. It's a fictitious product that we invented, but we did a real study collecting data on it. And here's the analysis plan. Now, I don't expect you to read it all now. As I said, we'll send you the recording, so if you want to look in a bit more detail, you can. The key real bit about most analysis plans is the planned tables and visualizations. And there's typically specific numbers that you need to calculate. Now, we have another webinar which talks about doing analysis and survey research in general. So I'm just going to emphasize a couple of key points here. The first is you really want to always work backwards from the goal of the study to figure out what analyses. If you just look at the questionnaire, you often go the wrong way. There are some frameworks that are important. I'm going to particularly focus today on something called the delta principle. And exploratory analysis largely comes down to, in market research, finding the key questions in your survey and cross-tabbing them with everything else. And we'll look through that as well. Now, one of the cool innovations in recent times is that AI is really good at creating analysis plans. Shocking to me that it is, but it is. So if you're bad at it, load your study and objectives and questionnaires into ChatGPT or whatever AI tool you like, and tell it to create the analysis plan. There's one principle that all good researchers know. It doesn't have a shared name. I'm calling it the delta principle, which I stole from some great UK researcher whose name escapes me. Very few novices work this out on your own. So if you're new to research, focus on this. It's pretty cool. When analyzing data that is inaccurate to some unknowable degree, create analyses that compare it to similarly inaccurate data and focus on relativities, not magnitudes. So that's the principle, best understood by example. Do you have a best friend at work? It's an unusual question, isn't it? When I ask it of my team in internal staff surveys, so many people tell me what an idiot I am for asking such a stupid question. It's quite remarkable how confident engineers are that how they are best at writing questionnaires, and that I, despite all my years as a market researcher, have no idea. And this one in particular provokes them a lot. So why do I ask it? Well, the legendary polling company Gallup invented this, and they've published great books of all the evidence to show what a great question it is, because it measures the extent to which people feel connected to data. But it's kind of a dumb question. It's clearly going to have a lot of measurement error attached to it. At one company, 16% of the company ticked strongly agree. What does this mean? Now, if you just try and draw a conclusion based on that number, you're in a bit of trouble because it's going to be a pretty dodgy number. It's clearly an unusual question with a whole lot of noise and ambiguity in it. How do we analyze it? The most common application of the delta principle is to just compare something by subgroups. And that's why market researchers and industry loves crosstabs, because that's what we're doing. So if 12% of engineers have a best friend at work, but 32% of marketers have a best friend at work, the difference between those two is called the delta, just the Greek symbol that means difference, delta. And that difference is actually much more reliable than the two numbers that led into it. Why is that? It's because there's clearly some error in terms of this 12% number, because it's a kind of dodgy question. Dodgy is in ambiguous, not dodgy as in bad. Poor language by me. Now, there's also going to be some error in the 32% of marketers here, this number here, but the errors in the two groups are the same. And so if we take the difference, those errors will, to some extent, and maybe a large extent, cancel out. Another way that we apply the delta principle is we compare to benchmarks, or we compare over time, or this is a bit more tricky, we create similar questions where these similar questions are believed to have the same error structure. So, as promised, most of our focus today is on data reduction. We're going to say we've got our analysis plan, we've done the analyses, and as I said, I've got other webinars on this, which I'll refer you to, and you're going to end up with lots of crosstabs. Lots of crosstabs means lots of data, and this is where the hard work starts. We need to perform data reduction. As the name suggests, the goal is to reduce the amount of data, chucking away all of the noise so that all that's left is the story. The Pope of the day asked Michelangelo how he'd carved this most famous of all of his statues. And he said, "It's simple. I just remove everything that's not David." And this is precisely how we find the story in our data. We just remove everything that's not interesting to our stakeholders. Or, returning to the fish motif that I introduced earlier, we reduce the quantity of the data, which causes the results to be distilled and concentrated. And so we end up with a much stronger flavor, much like with fish sauce, for those of you that like Vietnamese and Thai food. So how do we do this in practice? There are 8 techniques. We'll start with the first of these, which is to delete uninteresting analyses. So we're currently looking at the view mode of Displayr, which is what you use for presentation and dashboards. We're now going to go into the edit mode, which looks a bit similar, but here we can change and play with the data. So the survey asked people how likely they would be to buy the iLog. To use the jargon, we measured purchase intent. Purchase intent is another stupid kind of question. If you think about it, how likely is it that people can accurately tell you whether they're going to buy something or not? But again, the delta principle is our friend, and comparing with other data gives us insight. Now, this analysis that we're looking at here is showing us how likely people are to buy by duration. Now, this is duration of the questionnaire, how long they took to do it. This obviously is stupid analysis, something we should delete. By contrast, up here I have the planned analyses. So for example, we can see that 31% of people said they would definitely or probably buy it when we showed them the concept. And then when we told them how much it was going to be, this number changed to 23%. So delta principle again, minus 7%, minus 8% if I round properly. Now, the planned analyses that we've got here, they're going to be useful. And it's in the exploratory analyses here that we need to delete the garbage. So this one's obviously garbage. I could just manually delete it, but I've got 31 tables here, and I've been in studies involving thousands of tables, so I want to be a little more efficient. And the way I'm going to be more efficient is to automate. How do I do that? I'm just going to right click on this table here, and I'm going to go delete. And then I'm just going to delete any table that's not statistically significant. And statistically significant when you're doing exploratory analysis is a great way of automatically determining stuff that's not interesting. Now, I'm really lazy, so I want to delete most of the tables unless there's really strong evidence of something being interesting. So I'm going to choose this 0.001 or 99.9% confidence level. A lot of market researchers like to do this and spend more time manually checking everything. I don't. All right, so we just went from 31 tables to 15 tables, so we've got rid of half of it. That's a pretty effective data reduction. This table that's left is showing us age by purchase intent, and we want to reduce it further. Now, notice that this table has got 1, 2, 3, it's got 18 rows, and it's got 1, 2, and it's got 8 columns of data, so it contains 144 numbers. We want to reduce them as well, get rid of any uninteresting data. And the second data reduction principle is we want to remove clutter. And so I'm going to start by getting the clutter out of this table. Now, in this case here, well, the first thing I'm going to do is kind of arguably either clutter or uninteresting data. This first column, less than 18 years, I've got nobody in the study with that, so why do I want to look at it? I don't, it's gone. Typically, we're only interested in column percentages when we're doing exploratory analysis. And this is again for the reasons of the delta principle we talked about before. So this row percent and count, which have been helpfully put on the table, are just clutter or uninteresting. Gonna get rid of them. I've reduced it a lot. What else can we do here? The next thing I'll note is I've got this percentage sign, and that's really just a bit of visual clutter. They're all percentages, so it's redundant information. Note the intensity of this blue. We're drawn to the row and the column headings, but that's really just auxiliary metadata. It's visual clutter. So let's go with a much subtler format. In the olden days, we used to refer to the idea of reducing the amount of ink on the page. It's the same basic idea. There's some more ink on the page we want to get rid of, which is the caption at the bottom. It's not really helping me in this situation. Okay, so we've got rid of uninteresting analyses and removed clutter. What can we do next? The third data reduction technique that we're going to look at is to merge similar things. Now, if you look at these columns here, 18 to 24 and 25 to 34, they do have differences between them, but they're broadly telling the same story. And so I'm going to merge them because now I turned 10 numbers into 5 numbers. Getting rid of one of the columns. I've got clutter up here. I'm going to tidy the labels, more clutter reduction. Now, again, these two columns, broadly similar. Now, they're not identical, and some people get nervous about this. There are differences. I want to share them with the users. No, you don't. The whole point of data reduction is to find the signal, the big patterns. It's not the trivia. We're always going to lose information when we reduce data, but we're going to make it so much easier to digest. Cool. So now we're down to only 24 numbers, which is an 83% reduction of the data, and pretty impressive. We're going to do some more though, don't worry. So we've deleted uninteresting analyses, we've removed clutter, we've merged similar things. We're now on to changing the scale. In market research jargon, this is usually referred to as recoding. There are common ways of changing the scale. And we're going to do an example. Again, we're going to share this recording. So if you want to refer to this list later, you can. Okay. I'm going to start by putting an average onto the table. Oops. At the base of the table, I'm going to put the average. This is going to show the average purchase intent. Now it's showing that the average, and this is looking at the average of the underlying data, not the average of the columns above, is showing that the average purchase intent is 3 for 18 to 34, 3.7, and it's highest for the 55 or more. And this seems to make no sense, right? Here we're seeing that per interest in, but definitely buy was highest amongst the younger age groups. And here it seems to say the opposite. What's going on? Well, if you're an experienced researcher, you're going to know what's going on, which is that we actually need to look at the data. So I click the variable price and see how it's been scaled. And what we see is that in the raw data, people who said that definitely buy it have got a score of 1. People who said that probably buy it have got a score of 2. And this is because the way nearly all data collection tools work is that they just assign a 1 to the first category, 2 to the second category, 3 to the third. And so we need to change it. And we want to change it so that we give the highest score, the 5, to people who said they've got the highest purchase intent. This is called reverse coding. And when we do that, we're now seeing that we do indeed have something much more sensible, which is that the highest purchase intent is for the younger people. But if you think about it, these numbers are kind of arbitrary, aren't they? Why would we use 5 through 1? What can we say? If somebody says they're definitely buy it, let's assume that they're telling us the truth and they know their intention. That means they're definitely going to buy it. It's 100% chance. Probably buy it. I'm going to call that 75%. Not sure. Let's say 20%. Probably not buy it. Probably not buy it. I'm going to say 0 for these. All right, so now I'm putting my estimates of the actual probability. If I had benchmark data, I could put more refined estimates in here, maybe. So I click OK. And having done that, my average is now a forecast. So my forecast here is that 24.3% of people buy it. It's 41%, 41.5 amongst the 18 to 34s, 23%, 35s, and 55s are older. Now, some of you might go, cool, I've done a forecast. Yes, we have. But the delta principle is still dodgy data. So putting clever little scale numbers against it when we're recoding it isn't really going to solve the issue. We should just focus on the relativities of these numbers rather than this number. Now, this scaling is quite commonly done with concept tests, but there's actually a type of scaling that most market researchers prefer to do. So we're going to go back and I'm going to first explain it in a way that will surprise you, but then it'll come together. So most market researchers like to scale purchase intent by giving a scale of 100 or a score of 100 for definitely buy, a score of 100 for probably buy, and 0 for the others. And when we do that, we get a score of 42, 21, and 4% for these groups. Now, that is mathematically identical to just having merged together those two categories and created what's called a top 2 box score. We tidy the labels, which removes more clutter. So this number here is the same as that number here. We just calculate it in a different way. Top 2 box is just a form of recoding, or can be viewed that way, I should say. So let's tidy this little table up a little bit. And we'll take the average off the bottom because it's redundant. There's more information we can get rid of. I talked to you before about how this overall number is not that interesting. So I'm just going to hide it from the table. The bottom of the table at the moment is just showing me scores of 100. So that's completely useless. Hide that. And if you think about it, these middle points are pretty uninteresting. It's only the first row we're interested in. The bottom row is kind of opposite of the top row. So we can get rid of more. And it's kind of obvious which numbers are interesting. So the significance test is another form of visual clutter. Cool. So we started with 144 numbers. Now we're down to 3. It's really hard to miss the story in this table, isn't it? The next technique is to summarize. We can convert data to text. This used to be the privilege of the junior researcher or the minion or the intern, but now AI is our friend. So, now this is one technique you can't do in Q. You'll need Displayr for this. I'm going into the AI menu and I'm going to choose the option called interpret. It's because I'm going to give it quantitative data. We're going to rename this soon because it's a bit confusing that it's not called summarize. So I choose interpret. I'm just going to drag across all these exploratory analyses. So remember we looked at age before. Let's see what it can find on its own. Go AI. It's magic. And you might think it's slow, but imagine if you told your assistant to do it, much, much slower. Let's just tidy up the formatting of this a little bit. Okay, now it's actually, if you skim it, it's done a pretty good job. Like the age work, which you've looked at, you know that's right. I can tell you I've gone through the rest of it and it's pretty good. But one of the cool things about AI is that you can give it more informative prompts. So let's change that and we'll say, please summarize the tables. And then we're going to say, please, and I'm saying please because it turns out that if you're polite to an AI, you get better results, just like a human being. Not surprising. Please point any results that seem counterintuitive, inconsistent, surprising, or interesting to somebody who wants to launch an iLock, the iLock. So the product probably doesn't know what the iLock is, does it? All right. So, and it does this a little bit differently every time. I've got to warn you, it's not a consistent summarizer, much like a human being, but we've now got a great summary, and it's even pointed out a summary of the summary. It didn't seem to find anything particularly interesting or surprising. Nice work, AI. And we can also summarize as numbers. To use the jargon, we can create summary statistics. And we've already been doing a lot of this, as you'll know. We've been calculating percentages, means, averages. We're going to look at correlations. We've done top 2 box scores. The ones in blue at the top are the most common ones used in commercial market research. Now, let's work through some more examples. Here's a challenging table. Income has been measured in a lot of categories. What do I do? Fortunately, Displayr has got a great tool for automating this, and yes, this same tool exists in Q. I'm going to choose my income data. I'm going to tell it to create a new variable by clicking that plus button. There's lots of ways we can create new variables, but the most common tools that market researchers need are in this folder called ready-made new variables. And yes, we need to create some AI, and we are creating some AI to automatically select these for you. But at the moment, we need to know we're going to choose numeric variables from code category midpoints. And if you've got great visual attention, you'll notice a new variable got added into our data sources. Sorry, let's drag it across. There's little Macintosh bugs here. I don't know why my Macintosh keeps thinking that is useful to me. Try it one more time. Yay. Okay, and so the average income has been calculated as $63,000. Now, how has this been done? Well, we'll look at the data and we'll click values. And so what's happened in the background is Displayr has recoded the data. So it said if the person said under 1,000, it worked out that the good estimate was 500, which was the midpoint. 1,299, the midpoint's 199.5. So this is why it's called midpoint coding. It's a common technique. Cleverly, my colleague Chris, when he wrote this, has done it so that if it says 200,000 or over, it's going to go 224, so it's able to deal with unbounded stuff by looking at the other patterns here. And then don't know and refuse to answer have been set to missing values. And then we calculate the average. So we applied recoding or changing the scale and summarizing, which are the two data reduction techniques to get that number. For those of you who haven't done that before, here's all the worked examples of how that math works, and we will share that with you. You can do this in any program, not just ours, but ours does it with the click of a button. Here's some data looking at how many episodes people have watched of particular TV shows. I'll give you a moment to work out which TV shows are popular, and please enter them into the questions or the chat app in GoToWebinar. That's right. I need you to put your thinking hat on. Which 2 shows are watched the most? Pankuri, very fast, has come in and said Stranger Things. Yes, it's one of them. And Scott has said The Mandalorian. That's right, these are the 2 most watched programs. Now, this is just one table. Often you've got thousands of tables in market research. Took a few seconds. Why did it take a few seconds? Because there's 70 numbers, so it's hard work. we need to reduce the amount of data. Now, this is actually a simple analysis. When we're looking at TV viewing data in particular, we're usually not just interested in how popular a show is. We want to know what's called the duplication, which is how does viewing of that show relate to viewing of other shows? Because you want to create advertisements, if you're a marketer, so that you get to everybody. And if a whole lot of people who watch Doctor Who also watch Stranger Things, you would just choose one of those shows, right? So let's create a big cross tab. I'll drag, well, actually I won't drag across. I will, from here, choose episodes watched, cross tabbing the same question by itself. And now we have this monster table. Let's have a look at it. It's got 1,620 numbers. It's too big for my brain. So we need to do some data reduction. We'll go back to the summary table to start this process. So in both Displayr and Q, when you have categorical data, you can change it. And this is what's called an ordinal multi in Displayr, or be shown as a pick one multi in Q. And we're going to change it to numeric, or Q would go number multi. And when we do that, we do the values, and Q and Displayr go ahead and calculate the average for us automatically. So they're applying those two data reduction approaches for us. By now, you know we need to check the values. And here the values are broadly sensible. We've got the highest number for the highest frequency, but we can fix them. So if somebody, and make them better. So somebody said they've watched all the shows, it's 100%, 75, 50, 25, none is 0. What number are we going to start at one show? I'm going to give it a score of 10. Some people get very uncomfortable with the arbitrariness with which these values are entered, but you shouldn't be. This is a topic that psychologists have been studying for more than 70 years. And the conclusion that they've identified, and when I say psychologists, I mean psychometricians who analyze surveys used in psychology testing, like IQ tests and things like that. And what they've learned from this process is that as long as you're not an idiot, it doesn't matter what numbers you put in, you get the same answer. All right, now we can much more quickly see which shows are what most watch, which are The Mandalorian and Stranger Things. In the back of my head, I said Handmaid's Tale before. If I did, that was wrong. Mandalorian and Stranger Things. Now, what are we going to do next? The next thing we want to do is introduce yet another technique, which is called changing the order of data. Now, the simplest form of that, which isn't so profound, is to sort. But it always makes a huge difference, right? But we're going to remove a bit of clutter here as well. While we're here, we don't need this sum. It's not so helpful. And let's play around with the data. Rather than show the average, let's put on percentage share. Okay, now we've got something pretty cool. We're seeing that 28% of viewing by this sample was of The Mandalorian, 26% for Stranger Things, 9% for Picard. So we've condensed this down quite a lot. The story is much, much clearer. Let's go back to the main presentation. So we're looking at the 6-technique reorder. Sorting, very valuable. Here, before they were sorted alphabetically, by sorting from biggest to smaller makes a huge difference. Now, I love sorting in general, but reordering has got another thing that it's not just sorting, it's also a technique called diagonalization, which involves you take a table and you rearrange the rows and the columns such that all of the small numbers move into one corner. It doesn't matter which corner. Now, sometimes you'll have them in two corners, opposing corners. Now, this process is called diagonalization because a diagonal pattern appears in the data. In general, you'll find two patterns when you do it. You'll find a hierarchical structure like this, or a segmentation, which means you've got small numbers in both corners. Let's do it. So remember before we had this huge table of 1,620 cells when we cross-tabbed episodes watched by itself. Bad Macintosh. I don't know why it's doing this. If anyone wants to tell me in the chat, tell me. I'd love to know. So I'm going to cross-tab itself by itself again. And because we recoded the data to make it numeric and rescale the data, Displayr and Q does the same. It's like, we can just calculate correlations as our summary statistic. And so now we've got a table with only 100 cells. So it's vastly simplified. We want to move rows around to diagonalize. How are we going to do that? Well, the first thing I want you to note is that some of these things stand out. If you look at Doctor Who, it's at the bottom, but none of its numbers are that small, so we need to move it somewhere else. I'm just going to drag it up, and you do this in Q by dragging, and I'm going to put it underneath Star Trek Discovery. And so now we've got more small numbers in the bottom left-hand corner. What else can we do? The undoing is up here, but its numbers are pretty small. So I'm going to drag it down. We can see that Fargo is in the wrong spot. They're all wrong numbers, so or not wrong numbers, low numbers, so it should be at the bottom of the table. Okay, now I've diagonalized the table, so you can see I've got most of the small numbers in the bottom left corner and the top right corner. So this is what's called the segmentation pattern. It'll become even better though if we can get rid of all these 100 numbers, which we can by visualizing them as a heat map. So now we've gone from 1620 numbers down to no numbers. Let's increase the font size of this so you can actually see it. One of my amazing colleagues, Carmen, who created all these visualizations, she's got great eyes and she just loves small fonts. All right. Now, notice some pattern that's become much more obvious in the visualization, which is there's these two big blocks in the data. Segments. Remember I told you there's this kind of segmentation type of pattern in diagonalization? This is what we're seeing here. Now, we have the diagonal pattern, and the main diagonal is just showing the correlation of each show by itself, which is a correlation of one, not so interesting. But the fact that we have this big block here is telling us that the first 5 shows are relatively strongly correlated with each other. If we'd done a factor analysis, this may have been a factor. No, we'll think of them as a cluster or a segment. And if we look at what the shows are, they're all science fiction shows. So there's clearly a high level of duplication between science fiction. If you watch one science fiction show, you're more likely to watch others. And if we look within it, we can see we've got some stronger patterns. Picard and Star Trek Discovery have the strongest correlation between shows. And if you know your science fiction, you'll know they're both from the Star Trek universe, so that makes sense. Doctor Who's the next most strong correlation in this little cluster. Why is that? Well, these are what we might call the more nerdy or less mainstream science fiction shows. If we look in this second group here, we have a whole lot of correlation or another group, but it's a weaker group. The correlations are weaker, and particularly the one for Fargo is particularly weak. And U seems to be a little bit weaker as well. Maybe we should have moved little fires everywhere up before. So we've gone from a massive table of 1620 to a really insightful visualization through doing data reduction. The next technique we look at is to decompose, and I'm a big fan of this one as well. A decomposition is when you replace one number with multiple numbers. Now, this may sound like the opposite of data reduction, but stay with me. Sometimes you create decompositions by logic, and the classic example of this in business is the profit decomposition, where profit is revenue minus cost. So if you look at the revenue and the cost data separately to the profit data, you often get more insights. Revenue can also be broken up. So any company's revenue is how many customers does it have multiplied by how much do those customers buy multiplied by the price. In market research, we have one particularly famous decomposition, which is that the purchasing of product, how many products somebody buys, or equivalently, how many TV shows somebody watches, equals the proportion of people to buy that product, that is the penetration, or the proportion of people to watch that show, also the penetration, multiplied by the frequency with which the watchers watch that show. Now, in this data, we've got a slightly different style question. We don't know how many times they watched it, we just know the proportion, but we can still decompose it. And we can say that the average proportion of episodes watched by people is going to be a product of the penetration, how many people watch one or more shows, multiplied by the average proportion of the episodes watched among the watchers. Now, when we do this, a really interesting insight jumps out at us. So, as we've seen before, The Mandalorian and Stranger Things are easily the two most watched shows, and then everything else is much lower. Big jump between Picard to Stranger Things. When we look at the penetration data, quite interestingly though, the drop-off is much smaller. Yes, Stranger Things is 21 points higher, but that's nowhere near as big a difference as we're looking at the average. And when we look at the frequency of viewing the shows amongst the people that do watch, the real insight emerges. And what it is that The Mandalorian and Stranger Things have much stickier viewers. If people watched one, they tend to watch many more of the shows. Whereas Picard and the other shows, people watched and they're much more likely to drop out or much less repeat buying. So you can use theory to decompose data, and you should, and algorithms can do the work as well. But when they do the work, they tend to solve slightly different problems. Probably the most famous decomposition is the seasonal decomposition, where you can take any time series and break it up into the trend component and the seasonal component and the noise component to work out what patterns are underlying the data. We tend not to do this that much in market research. We tend to do, though, this particular algorithmic decomposition, which I love, and you'll have seen in lots of my previous webinars, called correspondence analysis. So we'll go into the visualization switcher, switch it out. I'm going to choose dimension reduction, which is where correspondence analysis lives. And there are various flavors of it. There's multiple correspondence analysis for raw data. There's correspondence of analysis for table, which is for any crosstab. But here in our table, we've got the same data in the row or the same labels in the rows and the columns, and this is known in the trade as a square table. So I'm going to choose a special form of correspondence analysis designed just for that. And now, when we're looking at this one here, and again, we'll play with some of our font sizes a little. All right. What we can see here is brands shows that are similar in the correlations or correlated with each other are closer together. Now, a few things to note. Let me just move this guy around to make it a little easier. Oops. I can't spell handmade is probably the thing that I'm noticing at the moment. Now, a few things to note here. We're getting slightly different results than we were getting in the correlation matrix. Now, a bit of it is that it's picking out patterns that we didn't spot before. So we've got this cluster of the nerdy science fiction shows, and we can see they're closer to Stranger Things, and The Mandalorian is a bit different. Amongst the premium shows, these three are closer together, and You and Fargo are less similar. So we're getting more insight, but we've actually lost a lot of information here. So in terms of the data reduction, right, what's actually happened here, the data reduction, we went from 100 cells in the initial table or the heat map, and correspondence analysis has turned that into only 20 numbers. So it's got rid of a lot of the data, and you might not think this shows 20 numbers, but it does. Each position of these different shows has got a horizontal and a vertical position, which are the numbers, and so that's why there's only 20 numbers here. Now, what correspondence analysis does very cleverly for us, it also computes how much information has been lost by the data reduction. And it's telling us that the horizontal dimension contains 47% of the information, the vertical 16%, and if we add them together, it's telling us that the total information explained by these 20 data points is 63% of the information that was in the original 100 data points. So we have lost 37% of information. And as I said, there is always this trade-off. The more you reduce data, the more the information is lost. We're usually okay with that because we're trying to distill the essence, but I will point out that some of it's material, right? We saw before that Picard and Star Trek Discovery are the most correlated. That's no longer clear here. We lost that little nuance in compressing the information as strongly as we did in our data reduction. The last technique is to apply common sense. Common sense comes down to three related things. Are results consistent with other findings that we have, such as other results in this survey or in other surveys? The second thing is the smell test. If the result smells fishy, it probably is. There's a lovely rule for this called Twyman's rule, which states that any result that looks interesting is probably wrong, and this rule, sadly, is usually right. The third secret is to hunt for apes. We don't want any apes. An ape is an alternative plausible explanation for the finding. If you can find an ape, then you need to kill it off, which means you need to either discard your analyses because the ape alternative plausible explanation is probably the truth, or you've got a lot of uncertainty, or you need to prove that the ape is wrong, which is what I mean by killing it off. Let's do an example. Here I have a table. We've got the purchase intent data again, and it's crossed by the person's love of technology. And we see a clear pattern, which is that the more they love technology, the more likely they are to say they would definitely buy. And it's easy to draw a conclusion, which is that the technophobes didn't like the iLock because they're technophobes. But what is an alternative explanation for that finding? Where is the ape? Now, some people hear this as a question about, what is the underlying variable which could explain this pattern? For example, it could be that age causes love of technology and purchase intent. That's not what I'm asking. What I'm asking is, what's the alternative explanation for this pattern, which means the pattern is not true? Feel free to type it in. Yep, it's another test. Type it into the GoToWebinar app. Can you think of an ape for this data? It's a hard one. Too slow. Look, I will share it with you. This ape applies to almost all market receipts, to all market research studies. So I'd encourage you to use it. Response biases affect market research surveys. Response biases are people's tendencies to have a preference for certain answers in surveys. One of the most common forms of response bias is traditionally known as the yay-saying bias. And this refers to the fact that some people like to choose the top box or the rightmost box more often, some the left, some the middle. The most extreme form of this we see is in flatlining, but it's a more general tendency. There are some people who are just more likely to say they like everything, some people more likely to say they dislike everything, some in between. Now, if we have this yay-saying bias in our data, it's possible that we would see a correlation between two things caused by the yay-saying bias, when in reality, if we had data with no dodginess behind it, we wouldn't find that correlation. And so now we've got an ape. Maybe it is that, in fact, we have this yay-saying bias, and it's not really that tech enthusiasts are more likely to buy their lock. It's just that people who choose the first option, are more likely to choose the first option. That'd be disappointing, wouldn't it? So here the ape is describing what that ape is. Now, there's a way we can test this ape. You see, if it's true that there are some people who just like to choose the first option in this survey, some in the middle and some the last, and not really reading the content, we should expect to see that with all of our questions. So I've cross-tabbed purchase intent by viewing in Fargo. And we can see we don't have any strong correlation in this data at all. If we look at the first row, 11, 16, 11, 6, 0, 100. So there's not any evidence for a correlation there, which is great because that kills off the ape. Yay saying doesn't seem to be affecting our survey, therefore it doesn't explain that previous result. Recap. To find the story in your data, create and implement your analysis plan, and then perform data reduction. There's 8 data reduction techniques. If you want to know more, we've got lots of resources, ebooks and webinars. Where do you find them? Well, you go to our website, displayr.com, click on resources, ebooks and webinars, and you'll find lots of them there. Or if you're not a customer, book a demo and we can show you how to do it. Or you can go pricing and buy. And from the pricing page, just click buy now, another option I'd encourage you all to do. What questions do you have? Please type any questions into the questions field and I'll answer them. Oh, that's an excellent question, Boris. It's like a planted question almost. If you noticed, there was something a bit unusual for Displayr users here. Let's go back and turn this back to a table. So one of the things that many users tell us when they switch from Q to Displayr is they don't like the way that most Displayr tables are on a page, because they just want a proper table. And we now have that as a feature in Displayr. You can just create a proper table, go plus, table, or even more briefly, plus table. Then select the rows. So we'll look at this, by this. And it creates really big tables that use the whole surface area of everything. These ones labels are a little bit too long, which is making this guy a little bit messy. Fiona asks, so would you be rotating the order of scales across respondents to counter this? And she asked that at 10:43. I wouldn't. It's a great question. So we're talking about the response biases, and this is something I think that people, this is a common misunderstanding, I think, in market research. So what people try and do is to remove yay-saying bias. What they do is they go, okay, they'll just take, they might randomize the order of things. So in one question, they'll go, they'll put, I would definitely buy at the bottom, and the other, they'll put it at the top, and they'll flip the orders around. For questions which aren't ordinal, where there's no clear ordering, they might randomize the responses. Now, there are times when there are sensible techniques to do, such as if I'm showing which party would you vote for, I might want to do that. But usually, I don't think they're very good for rating scales, and there's a couple of reasons for it. One is users kind of work a little bit on, respondents are a little bit on autopilot, and so they get used to the order of things. And if you change it up, they may just not even notice you've changed it up, and all your data gets massively corrupted. That's problem number one. Problem number two is, if they've got the bias and you change the scales, they're still going to have the bias. It's just going to be really hard for you to see it. So it's just going to mean sometimes the people who said definitely buy it, let's say you've got a person who likes to choose the first option. Some questions they're all going to be saying definitely buy it. Other questions they're definitely not going to buy it. And you're going to have this data which is going to go, the same person said they definitely buy it here and definitely not buy it here. That's very hard to solve and answer. So yeah, I don't think that randomization and mixing up scales is a great solution to these problems. They're hard problems. And that's all the questions we have. Thank you for your feedback, Fiona. Thank you, everybody who's a customer out there. And for the non-customers, remember, you can be a buyer too. Have a great day, everybody. Bye now.